Can everyone see that okay?
It looks pretty gigantic to me.
Pretty gigantic. Excellent. That's what we're going for. All right, cool. So yeah, I've just got a really simple starter project set up right now. I'm using Zeo 2.0 because we're getting close enough. I think after the hackathon we had last weekend, which maybe some of you got a chance to join, we got a ton of good contributions. We're like working our way through all of them. So I think we're gonna need one more milestone just to kind of get all of them in and make sure that everything's good with all of the changes before we do release candidate. But I think we're close enough that I'm starting to work more with Zeo 2, at least for these simple applications where I don't necessarily need all my dependencies updated to Zeo 2 yet. And so I think, yeah, it's already adding great content, which is awesome. It's like the better version of the Copilot.
Copilot is actually working in my thing now, so I'm just having fun prompting it. It's irresistible.
But the main difference so far that you can see here is instead of extending app, we extend this Zeo app default thing. And then we didn't have to do any of that like def run, like args list string equals anything. Like we just do this val run. We didn't have to provide anything. So it makes it a lot simpler and nicer. And I think Kit was the one who originally pushed on like, hey, we can do better here. And then John came up with some good stuff to do that. So that makes it really nice for us to just do these simple applications, as well as actually has some cool abilities for us to compose larger applications. And then the other thing you might notice here is this console is the capital C console versus the lower C console. And so we blew up that package structure where we had like a separate like console package and clock package as part of the new module pattern. And I think this also like looks super nice of, this feels exactly like you just had some like object console, and this print line is like just going to print something to the console. It feels like very familiar if you're coming from like an object-oriented background, but really this is returning a Zeo effect where I think I can, that was not good. Okay. So I'm going to try that one more time, and otherwise maybe my rewrite to braces, that's not what I want. Let's try one more time. Okay, all right, so I guess for some reason my type autocomplete is not working here. But if I did put in a type annotation here, this would be a Zeo has console nothing unit. And so this whole thing is just a Zeo effect that requires a console environment, and Zeo is going to provide one automatically, but you could even provide different implementations. So you get kind of all the nice benefits of these services that we've talked about before, but like it feels just super nice. And oh, I think I accidentally did that. That was weird. It feels very familiar. I think like you're kind of writing normal code.
So it also looks like println is back to returning nothing as the error message, as the error type instead of the IO exception, which it was.
Oh, maybe I may have. I'm also not compiling now, so I may have mistyped that here.
I see it is IO exception.
Yeah. So I need to, yeah, exactly. So I need to do an or die here. And that should, yeah, that'll be happy. And in fact, this doesn't even need the type to be nothing. So if I remove the type, I was just really not being honest with type. This is totally fine.
Yeah.
Okay, so anyway, that's enough like Zeo 2 intro. But today we wanted to talk about streams. And we thought this would be a good topic because we've hit on streams some, especially in some of our either earlier segments or segments that were more applied. So like where we did the Zeo Slides app, and we did some, I'd say pretty high level things with them where we were like broadcasting things and we were sending to WebSockets, and it was all really cool. But like, I think maybe you didn't get a chance to like see kind of how it's working underneath the hood, because it's just giving you this declarative high level interface, which is great when the problem you want to solve is Zeo Slides and not streaming, but maybe doesn't kind of give you like all the details of like, okay, well, what's actually going on with the streaming? And then we've done a bunch of segments, especially more recently, where we did the Zeo from scratch, where I think we've tried to build up a pretty good intuition of what's going on under the hood with Zeo. But we haven't really done the same thing with streams. And so I think there's a little bit of a risk that like they can seem like this kind of magical thing where like, okay, there are these operators and we use those operators, but like if something's not working or we don't have exactly the right operator, like we don't really know where to go. And what I hope we can take away from this is understanding more about what streams are and how they're implemented, at least one implementation, and not necessarily that you should have to or write your own stream operators, but that you should have hopefully a better sense of why things are set up the way they are. And maybe if you see one of these operators like requires you to specify a buffer size, like why does that operator need a buffer size? Or if there's a certain operator that's not defined at all, like why is that operator not defined? Sometimes maybe it's just we haven't done it yet, but sometimes there's some reason that it doesn't make sense in the context of streaming data. So that's, I think, what we're going to try to tackle today, if that sounds good to everyone.
That sounds wonderful.
All right, awesome. So let's start out with just what's the difference between a Zeo effect and a stream. So if I have, let's say, val my int is just going to be Zeo. Okay, so this is just going to return 42. So if I compare that to something I would get from a streaming API, what's different? Like, is a stream just like a particular domain? Like we could say, well, we have HTTP, we have streaming, we have all these things, and this is just like one different domain? Or is there something more fundamental about streams? And the way I would think about it is streams are incremental. So if you have a Zeo effect like this, it's either running, and it's just running. All you can basically know is that it's running, or it's done, and it's got either this int or this failure. There's no other state than those two. I'll create a Scala format file for you. There we go. And so we can even see this if we think about doing something like for fiber in my int.fork, and then we think about what I can do with the fiber. So basically the things I can do with the fiber is, if I want its result, is I can just wait for it. And so the fiber, like you can imagine, the fiber is doing some work. And you say like, hey, I'd like your result. The fiber is going to tell you one of two things. It's going to say like, hey, I'm in the middle of working, just leave me alone. I'll come back to you when I'm done. Or I'm all done, it's all perfect. Here's like the result, or here's the error. But there's nothing in between those two things. It's either in process and you've got nothing yet, or it's done and you've got the whole value. And for some things, that's like very logical, right? If we're doing like one network call and we're saying like, look, we want to load, some information about Kit from the database. Either we've got the information from Kit back or we don't. It's one of the two. And so that binary thing is a very realistic way of modeling lower level building blocks that we're putting together. But we can imagine that we have other situations where we are going to get results incrementally over time. Of if I say, I want all of John's tweets, well, maybe he's going to be tweeting a minute from now. And I could, if I wanted to say, well, give me all the tweets as of right now. But if I want all the tweets as they come in, he may never be done tweeting for a while in the future. But we don't want to wait for all the tweets. We want to like see the tweets now that exist now. And then when there are more tweets, we want to see those tweets. And so that's really, I think, the fundamental intuition behind streaming, is this idea of getting results incrementally. And I think the other thing that goes in there is this idea of being able to treat that whole stream of results as a value. So we could see the importance of that if we think about something like, let's say we do val my fake stream. And so now this is probably not bad. Let's do like maybe delay.
That's so crazy.
I know the Copilot thing is like really surprisingly good. Let's see, what are we?
We need to clock.
Yeah, exactly. And
int. Oh, can it fail with an int? Required. Oh, Z schedule int. Maybe we should just remove the type or regenerate it.
Yeah, let's do that. Let's see if that will work for us. There we go. Okay. Perfect. Okay. So this thing is kind of going to produce results incrementally. So like we can try running this now. Maybe I'm going to move this just down here so I don't have like issues with vowels being in the wrong places. So I'll run this. And let's see.
Maybe we should print.
Yeah, that would be good. Yeah, it very efficiently warmed up our hard drive there.
I can also do, oops, I could also delete everything, but I can also do console.println 42.
Yep. And so we see in a way there, we've produced these results incrementally of every 100 milliseconds we produce one of these, but we weren't treating these as values, right? Like in this case where we're print lining, like this has a return type of unit. Maybe at the end we would do like as 42 here, but all our return type here says, let me see if this will, oh, no, okay, so it's still not, oh, sorry, I did you. All right, so my autocomplete types is not happy here. But so all we get here is we get the type of this one return value. So we could theoretically do incremental side effects, but we don't have any ability to treat that sequence or stream of values as a value in itself and transform it. So like if I wanted to take this whole thing and I wanted to say like my fake stream delay, and I wanted to delay this whole thing by 1 second, I could do that. So I could just like shift the whole thing back 1 second. But if I wanted to, let's say I want to increase the delay between each of these print lines by 1 second. Well, I don't have any way to do that anymore because this is just one Zeo effect, because I don't have a value that's capturing this incremental production. I've just, by the time I'm doing this, all I have is this like one Zeo effect. So what we want to do is we want to get to a point where we can describe this value that is going to incrementally produce one or more things. So instead of just like the Zeo succeed, that's going to give us one int, it'll give us more than one int. And it'll give us those over time in different effects that we evaluate. So another thing we don't want to do here, another like kind of not great pattern, is we could say like my fake stream 2 is going to be, let's say, Zeo any nothing chunk of ints. And this will be like a chunk that succeeds with 42, 56, 78. So this is producing more than one value, but it's still doing it all or nothing, right? Because the Zeo effect either hasn't completed yet and I have no chunk at all, or it's completed. I've got all of these values. It doesn't have any way of saying, well, I've got 42 for you, but I'm going to eventually have 56 and 78 for you. So how do we go and build in this idea of incremental processing here? And I'm gonna walk us through one way of encoding streams. One of the interesting things is that there are actually a couple of ways of encoding them, and even in Zeo itself, we've used different ones over time. So there was one we experimented with before Zeo 1.0. Then there was what I'm going to go through today, which is basically the Zeo 1.0 streams encoding. And then there's a Zeo 2.0 streams encoding. But I'm going to do the 1.0 one because I think it's probably the most intuitive and accessible. And I think it gives a good intuition for some of the issues that are involved. And then depending on how we're feeling after this session, maybe we'll come back to this in the future. Maybe we'll make this a mini series and we can potentially explore some of those other encodings. Yeah,
I'd love to see that. I'm very curious about the new encoding.
The channel.
Also the old encoding, because I actually don't think I know. I think I have a vague idea of it, but let's take a look.
Yeah. So the way we're going to represent streams is, we could think of it almost as a effectual iterator. And so if we think about what an iterator is, like a traditional iterator in Scala, oops. No, that's not quite as nature. So it has this next and has next. Oops. And this, we probably don't necessarily work with it that much, I guess, maybe depending on like how much Java or how much low level code we have to deal with. But this is really the interface that underlies the entire Scala collections framework. So it ends up being even though it's very low level in a way, it ends up being very, giving you a lot of flexibility to describe a lot of operations. And it basically says, we can call this has next and say like, do you have another element for me? And then you can call this next, which is side effecting, which if there is an element is going to give you the element. And if there's not an element is going to throw an exception.
I want to see if Copilot knows how to write the for each method for it.
Okay.
It should be just, will it be able to do? Oh, yes, it did. Boom. Cool.
That's pretty cool.
Thought it would. But yeah, that's how you sort of write methods in terms of iterator. If you want to, you sort of while has next and you call next. So yes, it is partial. Next is clearly a partial function because if it doesn't have next, it won't exist, but you want to check first. And then clearly next is also side effecting. So it'll return the next value each time. So yeah, this is a totally immutable thing.
So let's think a little bit about how we would take this. So this will be our impure iterator. And let's start to think about how maybe initially we'll call this like a Z iterator and how we would start to make this interface more purely functional. So it's something we could work with in the context of Zeo and we could reason about in the same way that we reason about everything else. So the first thing we might say is this has next and the next thing is like pretty awkward because the contract is really, we're always supposed to call has next before we call next, because otherwise we could throw an exception. So we kind of have to do this like two-step process. We always check whether we have next and then we do next. And for like the very low level iterator interface, this kind of makes sense of you're trying to avoid doing that like option allocation, because you could refact this just to return an option. And then like the none would signal, well, I don't have next anymore. But then every time you get an element, you wrap it in an option. And so if you're doing very low level, like operations like iterating over an array, then okay, that doesn't make sense. But let's say for the purpose of doing this, that our streams, we're ultimately going to want to use them to describe things like getting tweets from Twitter. And when we're doing that, we're going to be doing all sorts of network IO. And so we're going to want our streams to be eventually as efficient as possible, but also there's going to be some overhead that has to be involved in doing this stuff. So maybe we're not going to be quite so worried about like doing everything in the lowest level way possible. And we'll also think we'll kind of add on abstraction, then we can optimize from there. So a really easy thing we can do here is we could get rid of this has next method, and we could turn this method into returning an option of A. And so now the contract would be, we call next, and it's going to either produce as an A value, which says, okay, I've got an A value. I may or may not have more A values after that, but here's at least one A value. Or I give you a none, and the none says, I have no values for you, and I never will have values for you in the future. I'm done. So that's okay. That's like going in the right direction. Now, the next thing we might say is, well, there was a thing I just glossed over a little bit there when I described that, which is what happens if I'm not done, but I don't have the value yet. So imagine that like I'm subscribing to this like stream of tweets. I haven't gotten an end of stream signal. Like there are going to be more tweets coming, but I'm in the process of doing the network call for the next tweet right now. So I have no tweet for you at this moment, but I will have tweets for you in the future. So I don't want to return none here because I eventually want to return an A because I want to give you a tweet, but I don't have the tweet yet. So what this interface says right now is that this is going to have to be a blocking call. That this, if I had this interface, this would mean that when I call next, if there's going to be a tweet, but I don't have one yet, I've got a block for the tweet. So we definitely don't want to do that. And we also, just from these parentheses, we know that this next thing is side effecting, that it may, like, when we call next, it's like, okay, they want another tweet. I got to go and I got to call the server and I got to get a tweet from the server. So if we're in the Zeo world, we want to make this an effect. So let's get rid of this next thing. And let's make this a UIF. So now we're getting a lot closer to the Zeo world. So now this is an effect that every time we call it, it doesn't even have to be a def here, it could be a val. So I could make this instead, I could make this final case class Z iterator. Next, let me just scroll down, make sure it still compiles for me. It does, which is lovely. I'm not sure why we're red here, but that's okay. Maybe I need to do my auto compilation. Maybe I'm actually not okay. Let's see.
Oh, just a closing brace. Oh, wait, we don't need that one. I think that's all good. Size.
Yay. Okay.
Awesome.
Okay. So now we've got something that's starting to look a little more like what we need. So now we have this next thing that says every time you call this, you can call this more than once, and every time you call this, we're going to give you back a value, or we're going to give you a none to say we're done. That's our end of stream signal. So let's just build this up a little bit more, and then we can try actually implementing some operators in terms of this. So the first thing that we can do with anything is we could do, I guess, what you call the Z treatment. So we've got the A here, but we might say, well, right now we have no way to represent that this stream can fail. It can give us the end of stream signal, which is one way of expressing failure, but right now that's the only way it can express failure. There's no way to differentiate. I reached the end of the stream, there's no more tweets for the stream you asked for, versus I got a network IO error, or you looked up a username that doesn't exist. And we'd really like to be able to distinguish those, because we know from Zeo that we have all this value from typed errors, and we don't want to give that up just because we're in this streaming world. So we can start to throw some E's around.
Yay.
We can give this an E. And we can give this an E. And so now this still works. And now this has a similar interpretation of I can call this next thing. And every time I do, I'm either going to fail with an error. And there's a little bit of, at least in this signature, ambiguity of the contract here, of you could potentially imagine a world where getting the error means you're done, right? That would be probably most similar to the iterator world, where like when it throws an exception, like you're done, it's not safe to use the iterator again. You could potentially imagine a world where like this means that like this element failed, but you could still call it again, and you might get another error the next time you called an element. The way that streams are encoded in Zeo is more the first way, where once you get an error, there's no more, you don't call the stream anymore. The stream is done with an error. So we've got the E, and then we can continue our Zeoifying, and we can give ourselves an R. And so now this stream can also use environment of every time we pull from the stream, maybe we're going to use the clock to delay, or maybe we're going to print something in the console, or maybe we're going to use some Twitter service that's actually going to abstract out the logic of how you asked for another tweet. This is going to give us the ability to use any service we want. So already here, we're pretty darn close so far to the encoding of streams in Zeo 1.0, which is pretty cool. That it's not some like exotic thing. I think you look at some of these other streaming libraries and like you look at the underlying representation, and I think most of the maintainers don't even really understand what the representation is. But like this, I think you can, we've spent maybe half an hour talking about this, and I think you can see how this is actually pretty intuitive. So there's one more step that we need for this, which is if we go back to the effectual iterator, this is the interface of the iterator itself, but if we're actually going to work with an iterator, we probably have one more thing we're doing. So let's imagine we have some object iterator and we have some make method. And the reality is that we're going to have lots of iterators that do lots of different things. But right now, let's just say this is going to give us an iter events, and it's going to have some implementation. Or you might even think about this as just think about doing to iterator on something. So there are times that you create an iterator. So even if I have like list 1, 2, 3 dot to iterator, this to iterator method actually is another method that has the parentheses after it, because this is doing a side effect of allocating mutable state. Because you can imagine if I do val x equals list 1, 2, 3 to iterator, and then I do y equals list 1, 2, 3 to iterator. No, those actually are both side effects. Oh, to iterator, or maybe it's just iterator. Sorry, I think
Boom.
So, ooh, well, nice.
Yeah, that totally is right. That's crazy.
So if I have 2 of these, and let's say I do like x for each print line, and then y for each print line. Right now, if I do this, this is going to print 6 times the console, because it will print 3 times for this and 3 times for this. But let's say I refactor this. So I say, well, these 2 have the same definitions. So why don't I just save myself some time and I'll just do that. And that's not going to give us the same result, because this iterator is a mutable thing. It's like every time you call next, you're changing the state of the iterator. So when we do it this way, we're only going to print 3 times instead of 6 times. So there's this additional effect of allocating the iterator that's not reflected just in the iterator interface itself, that's reflected in this from list method that Kit created, or that's reflected in this dot iterator method here. So that's the final aspect that we want to build in here. And so the simplest way we could do this is we could create one more Zeo that wraps around this. So we could do like Zeo RE, and maybe we call this outer one something like, we can almost call it open. So the idea of this is that we're going to run this. I guess we screwed something up. Oh, I think.
I don't know what happened. I'll use the from list thing.
Yeah, exactly. Get rid of this garbage.
There we go. Here we go. All right, there. Nice.
Okay. So now when we call this open thing, that's going to be like doing the from list. And so that's going to allocate this Z iterator thing. Then every time we evaluate this, it's like calling next. It's like getting the next value. And to get from this to ZStream, there's actually only one more step, which is we say, okay, well, we got this Zeo here to describe this, which is great. But we also want to be able to describe resources here, because we could imagine, like in this simple case, kind of this open action, all of it does is it just allocates this mutable state of like getting the initial, like, okay, now our index is at 0 and we're going to move 1 each time we're called. But in other cases, we might want to do something like we might want to open a network connection to like get the tweets or get the stuff from the database. Exactly. So like it's creating this like from file method that like, and yeah, GitHub Copilot is like doing awesome.
I don't know if this one makes sense, but you get the idea. Yeah.
No, I think other than maybe missing the import, I think that was like actually correct, which is cool. I guess there are lots of people who are writing boilerplate code to create iterators from files, which is probably correct.
Yeah, I just need the Java file. Yeah, that's crazy.
Yeah.
I'll comment that out. But yeah, I mean, so clearly we'd want to close the file once we, finished iterating over this. Yeah.
Exactly. And so we know we've got a data type in Zeo to deal with resources and opening and closing things. Anyone want to jump in with what that data type is?
Ooh, I know.
Go for it.
Int, no, Boolean. Z managed. Yes. Oh,
Yeah.
Tobias got it, and Naveed got it before me.
Yay. So yeah, we're just going to change this to a Z managed. And so this will give us the ability to model. So we open this stream or this iterator, and when we do, we're going to, that's an effect itself. It's going to allocate some state, and it may do some resource acquisition. Then we're going to get this thing, this basically next thing that we can call multiple times to get a value each time until it gives us none. And then when we're done with this whole thing, we'll release whatever resource we opened when we created this Z iterator thing. So this is really, really close to the actual implementation of ZStream in Zeo. There's only one slight tweak I'm going to do, which is having this option here is going to be a little bit annoying for us each time, because every time we pull a value, we've got to deal with this. Well, is the value a sum or is it a none? And probably like we don't actually want to call get on the option because that's not safe. So we'll map over the option. So like everything we do in this world is going to have like this one like additional layer of wrapping, which we know is going to be annoying for us. And it's also going to have some performance implication, which we said before, we were not going to be like, we're not just going to do the lowest level thing possible because we want to have this declarative resource safe API, but we also want to think about performance where we can. And I think one of the things that Kit's covered before is this idea of the number of possibilities and different ways of representing the same number of possibilities. And so one of the interesting things we can do with Zeo is if I have a Zeo that's a Zeo, right now I'll just say any string option of int, I can turn that into a Zeo any option of string int, and that's not right. But what is right is, I believe this is just Zeo2 dot sum. Let's check logic here. Let's see.
Oh, I think we have a what's wrong here? Oh, there's an equals here. There we
go. There we go. Perfect. So I can use this sum operator on Zeo, and I can just move this possibility of none from the value channel to the error channel. So we can think of, in both of these cases, we really have like three possibilities for how this effect can complete. It can either fail with a string, it can succeed with an int, or it can, in this case, succeed with a none. But there's basically three cases. There's, you can get a string, you can get an int, or you can get a none. And we can model those three cases in different ways. So like if I wanted to, I could even model it like in a third way of, I could say Zeo any nothing. Let's say I could do either string option int. These would like all be different ways to represent the same number of possibilities. Because if we look at all of these, they have the same possibilities right here. Now I've kind of taken this out of the error channel entirely, and I've seen, okay, in this case, you can get a string that's in a left, or you can get an int that's in a right of an option, or you can get a none that's in a right. But all of these have the same three possibilities. And so what that means is they all encode the same information, and we can choose which one of these representations we want to use based on other considerations we have of what we think is more elegant, or what we think is going to be more ergonomic, or what we think is going to be more performant. And so going back to this case down here with our Z iterator, a pretty nice move for us is to do the same thing that I did in the ZIO2 case here, of to move this option to the error channel. So I'll change this to an option of E, and I'll change this to an A. And so now the interpretation of this is going to be every time I get another value, I'm either going to get an A, or I'm going to get a failure that can either be an E or a none. And we're going to just say by convention here that if I get a none, that's the end of stream signal. That's saying there was no actual like runtime error that occurred, but I'm just letting you know the stream is done. You should do whatever you want to do based on stream is done. Definitely don't call me again. I'm done. I'm going to go take a break now and do something else. And otherwise, if I get an A, then that's saying, well, here's the next value. Feel free to call me again, and I may or may not have another value for you, and I'll give you another result based on that. Does that make sense so far?
Yeah, I like it.
All right.
Let you know if there are any questions on Discord. None so far. Or the Zoom chat, but yeah, none so far.
Okay, cool. So this literally is the representation of streams in ZIO 1.0. So when you're looking, if you go look at the ZStream source code, yeah, exactly. Change that to ZStream, and this in the, I think it's called process. I don't know. Open actually doesn't seem like a terrible name, but we'll call it process. So if you look at the ZIO 1 source code, this is literally what you're going to see when you go to ZStream. And there's definitely more complexity in how you implement certain operators in terms of this, particularly if it involves concurrency. But this is the representation. There's no secret from you. There's nothing else going on here. It's actually pretty straightforward. So I think that that's nice in a way that like there is some just inherent complexity domain of streaming, but once you understand this data type, I think it's pretty straightforward. And hopefully based on this conversation, you can see how we renamed it from being Iterator to ZStream, but Iterator is not a bad name for it. And it has a pretty deep connection with that original Iterator. And so if you think about like, if you're thinking about how do I do a streaming operation, it's not a bad idea to think about, well, how would I do it with an Iterator? And then probably that same logic you can do with a stream. You'll just do it with more flat maps and ZIO operators instead of checking whether you have a next element. But the same fundamental algorithms or logic or way of thinking about it can apply to those two. And so often like this Iterator representation can be a nice way to think about it.
Yeah, just to sort of try to label these concepts again, but the option E is kind of, this allows you to signal whether or not has next exists, right? By returning none. The next, which can be effectful, is encoded by this inner ZIO, and then the sort of constructors and the potential side effect full nature of the constructors is encoded in the Z manage that wraps everything. So that's kind of an elegant translation.
Yeah,
I did not know. That's awesome.
Yeah. And then the one other thing that you'll see in the actual implementation is that this gets changed from an A to a chunk of A.
Yes.
And that's a little bit of a performance optimization. So that in a way is a little bit less fundamental. But the idea of that is that when you do these streaming operations, often one operation can give you more than one value. So you can imagine, maybe not so much with one person's tweet, unless they're like tweeting a lot, but if you say like, I want all the tweets about Taylor Swift, like you might call that API, it might have 100 tweets for you about Taylor Swift since the last time you asked, because there are like lots of people talking about her. And if we wanted to, we could have each of those be a separate Zeo effect there. So like every time we call, we just get another one and we get another one and we get another one. But another concern we have is like, we want to be as performant as possible so that we actually can use this and we don't build a beautiful system and then have someone come back to us and be like, oh, your performance is too slow and you have to like rewrite the whole thing. And so making this a chunk lets us amortize this this cost of using the effect system, because every time we go through ZIO and we do another pull of one of these elements, we're hopefully getting a whole chunk of these elements, which maybe could just be one element, but could be 4,000 elements. In Zeo Stream, the default chunk size that we try to support if we can is 4,096 elements. So if you're actually doing chunking, you can really amortize that cost of using the effect system and make this much more performant. So that's the final thing you'll see there in the actual implementation. I think initially we won't do chunking. Maybe after we implement a couple of operators, we can look at going back and re-implementing them in terms of chunking, just based on time. But that's a little bit definitely good to know that it happens, and that can sometimes come up, but it's a little bit more of a performance optimization versus the fundamental representation of a stream here.
There's someone asked about sort of, Naveed asked whether or not this is, I think he used the word pull-based, if this is a pull-based streaming API, and it indeed is, right? This internal Zeo is kind of a pull operator.
Right, and one of the things you'll typically see when you're working with streams is we'll open a stream by doing this process. So I'll do something like process.flatmap, and that'll give us this inner Zeo effect, and typically that'll be called pull. And so this is a effect that, let's see if I get maybe I don't get a type on hover of this. Okay. Oh, right, because this doesn't even exist here. Maybe if I do, let's see. Let's see, is that, yes. Oh. I'm gonna try to also just do my spelling. Maybe not.
Oh no. Oh, it's all confused. Oh, metals. No, code highlighting is dead. Oh, is it because of, no, I don't know why. That's weird.
Yeah. I mean, I think we probably have one extra bracket, but I think my autocomplete is just not working right now anyway. Maybe this. Right. So I guess we're not gonna get the types on hover here, but think about this process, or like before we called it open, this is opening the stream, and then it gives you the ability to pull from the stream using this pull thing here, which inside another effect doesn't get like a label here, but typically we would call that the pull of the stream.
Yeah, and this is to contrast with push-based streaming, which works a little differently. I don't think we'll have time to look at that implementation detail today, but Zeo Streams is not push-based. Generally, these back-end streaming libraries are pull-based, and you'll see push-based streaming more on the front end, just due to sort of the natures of the problem. Pull-based streaming makes it easy to sort of manage back pressure. You kind of almost get it for free because the workers are asking for more work by calling the pull methods of sort of what they're derived from. So they're asking for more work, versus when it's push-based, imagine if you're a server or a barista and tickets keep piling up, people are giving you more work faster than you can handle it. You could easily blow up, instead of you going to your boss and saying like, hey, I'm ready for more work now, right after relaxing for a little bit. That's kind of a metaphorical distinction between them, but hopefully we can look at the implementation of a push-based stream later on. Obviously, I like Laminar, and that's push-based streaming, and sort of these other front-end frameworks. It would be fun to make a tutorial implementation of those sometime.
Yeah, and the pull-based streaming is a really nice fit for functional programming, because it gives us that essentially laziness, that when we do this, no work is typically going to be done unless we pull when we ask for it. And so, as Kit said, we get that back pressure built in, and we also get this laziness of these streams can potentially be infinite, right? I can create a stream that is, I ask for all the tweets about Taylor Swift in the world until the end of time, and that's a perfectly well-defined thing, and I can pull it and work with it as those become available, even though the whole stream will never actually be done potentially. And we'll see later, I think initially we're focusing on streams, but maybe either later in this session or in a subsequent one, we can talk about syncs as well, and we can talk about how streams and syncs fit together and putting together a whole streaming architecture. So, okay, we've got this data type. I think maybe the next thing that would be helpful is when we were working with the iterator type, we implemented some basic constructors for it. And I don't think we got a chance to, but we could have implemented some basic operators for it, like mapping over it or taking a certain number of values. So let's try to implement some constructors and operators for streams here. to get a better sense of how this could work. And we'll probably be a little bit less focused on performance here for some of these, is just exposition. But I think a fun initial one might be we could create a stream from an iterator. That would be a nice way to kind of show the correspondence between these two things.
Not quite there with the implementation. But
yeah, exactly. Not quite yet.
Type in there a little bit.
Well, and we're not doing we're not doing the incremental production, but that's okay. So I think this is a good signature for us. There's a little bit of a debate here of whether this should be like nothing or throwable.
Throwable, yeah.
I'd say like the iterator is like, who knows what the iterator is going to do. The iterator could come from who knows where and do all sorts of crazy things. But right now, why don't we stick with the nothing for that? I think that's like a nice simple thing here. Mm-hmm. And we're going to take this iterator, let's say by name, because just the creation of the iterator might involve some kind of side effect, and we'll want to wrap this up. And so let's think about how we would do this. So we need to construct this process thing. So I guess the simplest way to start is, okay, we need this case class, so let's make the case class. So we could say this is going to be Z stream of this thing. Don't know what it is yet. And then we know we need some Z managed that's going to allocate that's going to essentially do the making of the iterator. And then we're going to have some inner state that's going to pull from the iterator. So in this case, the making of the iterator is just evaluating this. I mean, this is essentially a thunk here. Like we're using this by name parameter to make this a little bit nicer, but really we could, if we wanted to be super explicit, we could write this like that. Mm-hmm. Maybe I'll go back to it being like this. So here, I could just do Z manage succeed iterator. And so this succeed is going to suspend, this is going to be another lazy, well, that's not right, but this is going to be another lazy operator that's just going to suspend the construction of the iterator and give me this Z managed. And so now that I've got this iterator and I've suspended that, I could map over that. And so now I've got this iterator that's been allocated. And so now I'm in here. And the type I need to return in here is this Zeo, in this case, any, nothing, option. No, sorry, any option, nothing, A. Yep. So let's think about how we would do that. Mm-hmm. So we know our two operators are this has next and next. And we know those are affecting, and we need to return a Zeo. So why don't we do, well, we can't quite do Zeo succeed. So why don't I do Zeo, first I'll do Zeo succeed iterator dot has next. And so that'll give me, and then I'll flat map that. And again, this is not necessarily the most performant way to do this, but I'm just gonna do this right now. So I've checked where the iterator has another value. And then if it does, I'm going to succeed. I'm going to call next, and I'm going to return that value. And if it doesn't, then I'm going to fail here.
Fail with none, meaning basically
end of stream, because that means that the iterator said it does not have more values.
Gotcha. Yeah,
so now I should be able to comment this out.
For my perusals of the Zeo streams codebase, I think there's even like a little helpful companion object inside of here called pull that has sort of some definitions like stop on it that will just return a Zeo.fail of none for you, so that you can work it sort of, give it a more semantic name.
Yeah, why don't we, we can even do that right now. Yeah, I think that's a really nice way to make this more clear. Yeah, maybe we'll call this poll.end.
Poll.end, that's probably is, yes, exactly.
And we call this like poll.emit maybe? Or succeed.
Poll.emit, let's do it, yeah. Emit A. Not quite there, nice try. And that's just simply Zeo.succeed. Okay, okay.
So let's try, I think we threw something.
Oh, I have to do an equals. Yeah, the colon equals.
It's a good sign. Most of our problems are like our own typing mistakes and not. All right, so yeah, now we can get rid of that.
And we don't have to have the comment. Lovely.
Yep. And so there we go. So now we've converted this iterator into a stream. So I think another good operator to probably implement here would be something that's actually going to run this stream, because then we can actually like start to do some things and like show some howdies and stuff and make this a little bit more interactive than just code here. So one of the things that becomes a little bit different with a stream versus with a Zeo is there are different interpretations of what it can mean to run a stream. So running a Zeo has this like really natural interpretation of like, it's either not done or it's done. If it's done, it already has an A or an E. So the pretty logical interpretation is run it and give you either the E or the A. And okay, maybe you want to throw them away, but it's either, if you want to run it all, you want to run it for the E or the A, versus the stream, because it has this multiplicity of values. You could want to run it for its like, maybe you only want to run it for its first value. Maybe you're doing some like math filtering thing where like by the time you're done, there should only be one value that kind of matches your filter predicate. And like, once you find that one, you just want to like go through the stream until you get that and then you're done. Or maybe you have something where you're like, look, I want the first 100 values, or maybe you want all the values. So there end up being some different stream operators you can use for running the stream.
And they're very similar to collection operators, right? Because you can sort of view the stream as a collection.
Yeah, exactly. So why don't we start by implementing one called run collect. That's just going to collect all the values. So this is, it's not, we won't want to call this itself on a infinite stream, but we'll see later on, we could use like a take operator, say, well, only take the first 100 elements, then we could run collect those. And there'll be other ways we can run the stream, but this will just kind of give us one like simple one. And this is not the right
It's right.
Pilot, but I appreciate the thought. So this is going to give us a Zeo, yeah, very close to that, but well, it's going to give us a chunk instead of a list, because like it's chunk. And this definitely is not the right implementation. So, okay, let's think about how would we implement this? So really working backwards, or maybe working forwards, the only thing we've got is this process thing. So we've got to use this process thing. And if we go back to the analogy of process as being like making the iterator, the first thing that we've got to do is we've got to, before we can like collect all the values from the iterators, we've got to make the iterator. And so the way we do that is by evaluating process. And here, since we're returning a Zeo and we don't want to stay in the zmanage world, we'll actually call process.use. And so that'll give us this pull that we can evaluate.
Mm-hmm.
So this is like make the iterator and then give me the iterator interface. And right, we said this pull thing was like calling next on the iterator, except it gave us an effect and it handled the possibility of the none value as part of this failure type of the Zeo versus is just having to do that weird has next and the next thing.
Mm-hmm.
So, okay, so now conceptually what we want to do is we want to just like keep repeatedly calling pull until we get none here. And the one a little bit complication that we have is that we need to maintain some state, because we're going to be like pulling this thing multiple times, and we need to put this together somewhere. So we could do this with like a recursive function, but I think it may be a little bit easier, at least for this exercise, if we think state, like a very easy thing to do is we can just allocate some state.
Make a chunk builder.
We can do that, or yeah, I think it's a great way to do it. We can also do like a ref, but yeah, so let's do chunk builder dot make. And so that'll give us a builder here. And then, yeah, maybe we'll actually loop here. So we could do something like we could say val loop is going to be, so we're going to pull on this, and then we're going to, let's say we're going to fold over that. And so we're basically going to have two possibilities. I'm just going to like sketch this out a little bit first. So this first one is going to be the error. And so this actually itself has two possibilities. So we could say, okay, sum E. Oops.
Was weird stuff happening?
Yeah, exactly.
Okay. Oh yeah. Oh wow. Yeah. I typed some stuff. I don't see it on your screen though. So.
Oh really? Okay. Are we out of sync? That's not good. So this indicates the stream failed with an error.
Mm-hmm.
We've got none, which is stream end. And this is an A, which is just stream emitted an element. And so let's think about how we want to handle each of these. So if we got an E, then I think we just want to fail with that E.
Mm-hmm.
If we got a none, then we don't need to recurse anymore. So we just make that Zeo.unit. And if we got an A, then we need to add the A to the chunk builder. So we could, in effect, if we wanted, builder plus equals A. Let's see, I think we got some kind of, oh, because we need to, the builder needs its type. So it's be A. Okay, it's happy.
And in this case, we don't, okay, well, I'll wait and see. I'm curious.
And then we need to recurse here.
When we call, maybe for the end case, do we not want to sort of say succeed of builder dot build or whatever? I forget, make chunk, or I forget the method. Are we going to do something slightly different?
Yeah, so that's a great way to do it. I was actually just going to do it at the end. I was going to do like loop.as builder.results.
I see.
But yeah, I think that's a lovely way to do it.
If I used the wrong method, is what is it? Result?
Yeah, I believe it's result.
Okay, and then we need a type here, maybe not.
Yes, we do need a type because it's recursive. So this is going to be a Zeo R. This can no longer fail with the options. So this is going to be E, and now this is going to succeed with a chunk of A. We did the builder.result, I believe.
It's basically return the loop then, I guess, right?
And let's see. I think we got some.
Do we have to make it a lazy bell?
Yes.
Okay.
Perfect. There we go. Okay. So
nice building recursive effects because you don't need to sort of do the usual business. You just make it a lazy val. You could refer to yourself. It's what a beautiful day.
Yeah. So now I think we've got the infrastructure to at least start running a small example. So let me grab my run function from up there, and I'll bring it down to the bottom here. And we'll check ourselves here. So now we could do something like, so let's say val stream, val my real stream, let's call it. And so this could be Z stream. And now that we gotta be able, this is not the real Z stream, this is our little fake one. But yeah, let's just do list 1, 2, 3 dot iterator. Okay, so that's gonna give us a stream here, hopefully. Let's see what's, oh, we defined our own, oh, so we We need to, I think.
I have
comment on-
iterator.from list should work actually. So let me.
Oh, okay. All right. We'll do that. Well, I think we have a problem here because this iterator, it thinks it's our iterator that we were playing with the Scala iterator.
Oh, I mean, that's fine as long as.
Oh, yeah, I guess fair enough. Fair enough. We can. All right. So we'll go from our iterator instead of Scala iterator to the stream. Okay, perfect. All right. So that's going to give us a stream. And yeah, this is not. So then let's write a little program here. And we'll start with a really simple one. So a really simple program would be, we could say, for chunk in my real stream run collect Zeo debug chunk. Cool. All right, so let's see if we can. Let's give this a shot.
Uh-oh, 344. That's not even a 59.
Not implemented. Where are we now?
Oh, I'll delete these guys.
Oh yeah. That's this is why it's good to use lazy vowels when you're showing how types work. And there we go. We got chunk of 1, 2, 3. So that's pretty cool. So we've gone from like, oh, what are these stream things to like, we've defined the stream. We took new data and we brought it into the stream, and then we ran it from the stream into a normal data type. So that's pretty cool.
More methods.
Yeah. So let's do a couple of stream transformation operators, because there's not like the streams aren't that interesting if all we're doing is just returning them. And then maybe we can also try to do something like that from file one. That maybe could be an interesting one, because that would let us do like the resources. But yeah, so let's start with maybe something like map. So what would map on a Z string look like? So we know kind of what the signature should look like. It's going to be F, A to B, and it's going to give us a Z stream REB. And I think Copilot may have taken away my my reveal. But so what we start to see is there are definitely complexities and like cases where we have to do like more work. But one of the nice things is we can like take advantage of the existing functionality that's defined on these other operators that we're like using. We're building on ZManage, we're building on Zeo. And so like if I want to map the stream elements, well, all I do is I map over that process thing just to be able to transform the pull. And then I map over the pull and I say, well, every time you pull a value, transform it with this function F. And so just with that, let me do my real stream dot map times 2. Let's run that.
Yay.
Yeah. So that one was almost too easy. Why don't we try to implement something like take? So only take a certain number of values from the stream. So how do we implement take?
Yeah, these are more interesting, the ones that sort of change or run the stream or transform.
Right. Yeah, GitHub Copilot is trying to, but that is not valid because there's no take on the process. Yeah, something where you exactly are kind of changing the structure of the stream. How do we do this?
That's interesting. So I think it's going to look a lot more like, so Anivita is a ref.
Yeah, we're going to have to use some kind of state internally to do this. And so sometimes we can have trade-offs of like, do we do it with a ref, or do we have some like here, we just allocated some mutable state of our own. But I think ref is kind of a nice pattern to use here. So first thing we know is we need this Z stream thing, because the Z streams all was defined in terms of this process thing. And then typically when we're working with operators that transform existing streams, the first thing we need to do is we need to open those streams. So like here, like an initial thought is, okay, I need to open the original stream. And that's going to give me the pull. And then I want to do something with it. And I think as we were just saying, a lot of times we may need to maintain some additional state in here. And so sometimes we can do it with some kind of just like either here we had mutable state, or sometimes we could do it maybe by threading like a variable through here. But one thing we can do here is we could just like allocate a ref with some state. So here I could say ref.make, and maybe this will just be 0 initially. And then I can zip it with that. And so then I'll get two things. I'll get this ref, and I'll get a poll. Let's just say, let me get my compilation going again.
Do you want the map there? No, we don't. We don't want that. I just want.
No, sorry. I want the map after it.
Do we have to do this? I guess to managed on the ref as well, right?
Oh yes, thank you. That's right. And then we need
manage type
up here and case there. I think there we go. Okay. Okay. So now we're saying every time, and so what I have to return here is the new poll. So this is like this first part, like you can think of the managed part as like the setup of like, what do you want to do before you like start pulling values from the stream? What's the state you need to allocate? What do you need to do to just get the board arranged the way you want it to? And then in here, you're always going to return this poll thing, this Zeo R option E A, or chunk of A in the real implementation. And this is going to be what it means to pull every time, what we're supposed to do every time someone asks for a value from us.
And I'm guessing that we don't often change the managed because we can sort of just, I'm guessing most of the functionality just delegates to operations on managed if it concerns managed at all, right? Because the actual, what's unique about streams is this multiplicity, and that's sort of defined on this inner Zeo, right? Are there any interesting operators that transform the managed in some strange ways?
No, I think you're exactly right that like we've got that functionality for the managed. So I think in general, the most you'll see is that like there'll be operators that like delegate to the managed. So like the managed has the functionality to like add a finalizer. And so you can add a finalizer to a stream and it just calls add the finalizer on the managed.
But it's going to look like this kind of, you just delegate.
Yeah, exactly. I think the one thing that can sometimes get a little bit more complex is just particularly when we have concurrent operation on streams, like when we want to close those intermanaged. So like ZStream flat map gets like, you have to think a little bit there about like, because you have this outer stream and then every element of the stream, you open a new substream and then you evaluate its substream. And then when that substream is done, you've got to close that substream. And then you go to the next element, you open a new substream and you kind of do that. But generally those are like taken care of you in terms of the ZStream operators. So I think really the only time you have to deal with that is if you feel like being a Zeo contributor and you want to do PRs for low-level stream operators. So, okay, so here then we've set up this state for ourselves of we got this ref that has how many, and I think the interpretation of this is going to be how many times we've pulled so far. And then we've got the poll that says, okay, we'll give us the next element. And so I think what we could say here is, I always find it nice here to just think in terms of like limiting cases. So we could say, if we do take 0 or take -1, then we shouldn't take anything. So we might start by doing ref dot, maybe we'll want to do this atomically, say, let's say, maybe we'll say ref dot get an update. And then we'll flat map that. So this will give us the number of times that have been pulled so far. That's the interpretation of n here. And so then we might say that, or we shouldn't use n because we're shadowing that n. So why don't I call this I? And so we might say if I is greater than or equal to n. So in other words, if we've already taken as many elements as we should, then I want to do the end of stream signal, and I can use that nice thing. I can take advantage of what you wrote for us. So I can use poll.end there. And then Otherwise, I'm going to go ahead and do the pull.
Just need to import stream pull because it's in the companion object there as well. Okay, so
Okay. And then I think I can take this out. And so that's actually the implementation. It ends up being pretty simple here. And so, yeah, I'm sorry, go ahead.
Oh, sorry. So I'm guessing we want to do it safely here because unlike run collect, we could kind of get away with this builder because we know that we're not going to be calling this, like this is the new pull method. And we're going to be calling this potentially concurrently in lots of places, whereas this is sort of just a one-shot operation down in run collect, right? So you can use sort of some more mutable tricks. You wouldn't want to have like a var count 0 here and do the sort of just a mutable thing, right? Because, well, that might be a little more dangerous. Is that correct? Like in doing something.
Right. So one of the things that we get to with the more advanced stream operators is, like, I think so far we're working in what you could call, like, I think the most prototypical streams way of you're processing the stream incrementally, where you take one element and then when you're done with it, you take the next element. But you can have some operators where you have to say, well, would you want to be safe to be pulled concurrently? So right, so this is safe for being pulled concurrently. But the other thing that's nice about this is you can see that each time you implement one of these stream operators to transform streams, you only have to worry about defining one pull. So like theoretically, the person is going to be pulling over and over again, but we didn't really have to worry about the logic of like every pull. We just had to worry about the logic of one pull. We said, like, whenever you pull, do this thing. Mm-hmm. And here, like, we only return pull once. We didn't like recurse and say pull again, because that's not our responsibility. It's the person who's pulling from us who is going to call this whole thing again if they want 2 values instead of 1 value.
It's really beautiful in terms of sort of showing the how composition pays off, right? We're sort of delegating to more powerful primitives or when we need to, and then we only need to alter just a little bit of logic that is important to the semantics for this operator, and then we can sort of just delegate to the rest, and that's a good powerful example of FP.
Yeah, so let's test our example here. So let's say I do map to dot take 1. Let's see if we got this working right.
And there I'll add a few more.
Yeah, I'll change this to 3 now that you added more elements, so that this will actually be a little more interesting. Wow. So there we go. So we only took the first 3 elements. And yeah, go ahead.
A tap real quick, because I bet tap is gonna, maybe that's auto-completable.
Yeah.
Tap, can you do it? Almost, except no, it's gonna be a function from A to Zeo. Okay, let's just say UIO of unit or UIO of any or something, just to make it boring. Is that happy? Oh, not quite, because we want to map over this and change. We want to call some side effect for each element.
Right, and in a way, you're getting one of the interesting things about the stream is you have these 2 effects of you have the open and you have the pull. And so you could imagine, like, I mean, I'm not sure really be the most well-defined or useful operator, but you could theoretically have tapped the process and that would like say like, tell me what you got from that. I mean, it would just be this Zeo effect, but you could do something on kind of the open versus on the pull. But I think you've got, the most logical interpretation there.
So let me do,
yeah.
Okay, so let's see what happens there, because we could tap multiple times.
And you're gonna, I think this will be really interesting as well. And we can illustrate something else once we resolve.
Oh, print, oh my gosh. It's nice. It's like print lines.
Yeah, 2.0, baby.
Heck yeah, okay.
Yeah.
Oh, okay, now what? Oh, because I've made it such that I can't change the error type. That's my.
Why don't you just do a Zeo debug?
That's right, Zeo debug. Okay. Cool.
Okay.
Zeo debug. It's basically console print line, except it doesn't add the environment, so you can't sort of swap out implementation.
Not as principled, but very useful for exercises like this.
Yes.
And why are we off here?
Is it off? I don't see anything.
Oh, hold on. I don't have the auto. Oh, sorry, I don't have the auto compile going here. There we go. Okay, we're perfect. Okay, so yeah, so let's run this. And I think this will be really interesting for us. If we find streams interesting, but I guess I did.
Oh, interesting.
And let's.
Okay, we did take one. Duh. Okay.
Why
Yeah.
don't we take 3? Yeah. Okay. That'll
I was confused for a second there.
Yeah.
So yeah, wow 1, bigger wow 2, wow 2, bigger wow 4, wow 3, bigger wow 6. Awesome.
So yeah, so there's something really interesting in this sequence of what gets printed out. I'm actually just going to make this bigger a bit so we can see it all. So this is illustrating one of the really cool things about streams, which is that incremental production and the way that these operators get applied incrementally. So if I think about it doing something like if I had list 1, 2, 3 dot map blank times 2, and then I guess we weren't really doing something, but well, I guess I can.
There is no tap, unfortunately.
Yeah, I know. I was like, will I cheat and do a tap? Or let's just do. I mean, I could do it like twice here, maybe, but not 3 times. That's too much. So when I do this on something like a list is strict, and so what this is going to do is first it's going to map over the whole list with this times 2, and so it's going to reduce that to list 246 dot map times 2. And then it's going to apply that second map.
I could sort of make a fake tap just by doing.
Right.
It.
If we wanted to, we could do the fake tap. Yeah, exactly.
So print line. Maybe that would be nice just to see.
Yeah, I think that'll. Yeah, that's a good way to make it concrete.
Is that happy? What have I done? I think I should be. Oh, I need to do no outside of this. So colon A, and then let me just copy. Oh, come on, Vim. All right, I'll just cut you.
Well, I think if we do that, we won't even need. Oh, well, yeah, we'll need 2 taps, right? We'll tap, we'll map, we'll tap. We'll do the same thing we did. And that'll be very, very nice and clear.
Yeah.
Okay. All right. So now let me get rid of this. Oh, and so this should. Okay. And should we call these different things like list wow or something?
Oh, sure. Yeah, list wow is good. Will it run this at all though? Maybe we should put this into second equals notice the UIO.
Yeah, that's nice.
And yeah, you can put a LWow or something. And then we can do this after the debugging, we can just do second. Okay, let's try this. Oh, it should be lazy del as well. All right.
Okay, so let's look at the list wow first. So this is, I think, what we might expect and what I was saying of with the list, it's going to do the whole first mapping first. And then it's going to do the whole list mapping, and then it's going to be done. So we're going to see how we got like list 1, 2, 3, and then we got 2, 4, 6. And now contrast that to what we got here. So here we see them being interleaved because the stream is going to produce them incrementally. So the stream is only mapping over the values that we're taking. So what the stream is doing is it's saying like, okay, you asked for the first value. Well, okay, I'm going to tap it, and then I'm going to multiply it, and then I'm going to tap it again, and then I'm going to give it to you. And then, okay, you asked me for another value. I'm going to get it. I'm going to tap it. I'm going to multiply it. I'm going to tap it again. I'm going to give it to you. You asked for a third one. I'm going to do the same thing. And so it's never going to evaluate. It's going to do that incrementally for each element. So it's going to process one element, then process the next one all the way through. But also it's only going to process what's needed. So we could make this even more clear if let's make these lists the same. So let's take this 1, 2, 3, 4, 6, 7 here. Do this again. So notice how the stream, it only mapped over the 3 elements we were interested in, even though the take wasn't until after we were doing the maps and the taps. Versus
take at the end here, and it won't matter.
the list, Right, it doesn't matter because we're not doing the take till the end. The list is eager. The list, as soon as we do any of these operations, they're actually happening. And so even though we were only interested in 3 elements here, we still did these things for the whole list. And so this gets to like another way that like the stream can be interesting in letting you describe these things in a very declarative way of like, if I'm working with these tweets, I could describe all these operations over this like infinite stream of tweets. I could say for every tweet, get out this thing and redo it this way, and then put them together and do this. And then at the end of all that, I might say, we'll do that until you found the tweet with a smiley face. And it's going to do the whole logic. It's going to only do it until it finds its tweet with a smiley face. So it lets you describe things in a very declarative way.
And I think at the beginning we were saying now we can sort of add something like tap, you know, and we could add a delay in here potentially. Is that sort of like Zeo?
Yeah. Why don't we do a delay? I think that's that's a great one.
Let's add 500.millis here in between each call, and I'll do it before. I guess it doesn't really matter, but let me do it before. Yeah, I'll do it here. Let's see what happens. Yeah, what happens now if we run that?
Yeah, let's run it.
Yeah, cool. So we're able to space out even after we have defined everything, which is exactly what we were sort of saying at the beginning, which is kind of cool. Another cool feature of Zeo too is that you don't need to import the Zeo.duration.underscore.
Yay, or Zeo.clock.
Yeah, or Zeo.clock. It's all just here in the sort of the underscore, Zeo.underscore. Should be a little nicer, especially for knocking around experimenting. Especially for Symposium. It's all about how nice Symposium is.
It's good to dog for you stuff.
Yes. Cool. So that's pretty powerful.
Yeah. Do we want to try to do a from file one and then call it a day here?
Let's do it. Oh yeah, we got the 6-minute challenge. Quickly, Adam.
All right, so let's go to our constructors.
I think up here. All right. Just give Copilot a chance.
Okay, so this time we're gonna have a file. It'll just be, I guess, maybe it can be a string or a file. I guess
string is fine. I haven't imported the file correctly yet.
Okay,
so
perfect. Okay.
We'll need
and then this time won't use environment. We'll use throwable for the error type because we're doing easy stuff. And I guess we should. So maybe we should call this like lines or something. We have to kind of decide what we're going to get from the file.
Yeah, let's get from file lines. Yeah.
Yeah, let's do lines. Let's call it. This will be string. Okay. So the first thing we're going to do, and I mean this might actually be a nice other area where we could be compositional, is ideally we would just have a Z managed lying around somewhere that like opened a file for us. Which I think may actually.
I think there is one. It's a bit low level actually. This would probably be something that we can have a little higher.
Okay, well, maybe we'll just do it ourselves right now. So I can do cmanage.make, and then.
Ooh.
Okay, that's not bad.
Buffer reader, new file reader. Whoa.
Okay, we'll create a reader. We'll close it with the reader.
And that's flat mapping. Okay.
Yeah, most of that is not terrible. This just needs to be a Zeo, but yeah, that was not bad.
We need an extra closing line here. Let's see, does this, there we go. That'll format itself now.
Okay. Let's get some autocomplete. Yeah, but I think between the Scala compiler and this, it's nice. Okay, we need some.
Can you import these types? I don't really quite I forget the paths. I'm so used to.
Yeah, is it what? Import Java. I know I'm not getting java.io.
Find it. So we need file reader and buffered reader. All right.
Yeah.
Where are you? Oh no, I quit IntelliJ. Is that right? All right, nice. And then the same with file reader.
Yeah.
Is it happy? Oh, good, almost. Okay, cool.
Okay, and then I think we don't want a flat map because this is a Z managed, so we just want a map there. And wait, I thought I just fixed that. What does this say?
Or do we want to use? No, we don't want to use it either. We want to map it. Yeah, exactly.
Yeah, we want to. This whole thing needs to be in a Z stream.
Oh, totally. Yes. Okay, I'll add the closing paren.
Perfect.
Huzzah.
Let's see.
Oh, and we have throwable, but we need an option throwable, so we need to wrap it in sum then. Okay. Oh, and there is the case where.
Right, so I think if the reader is not ready, I think that we actually fail with none. And we'll just use a ZIO attempt constructor, and we'll say if something gets thrown anywhere, then we'll just. So I think this can be, yeah, this doesn't.
It's only going to read one line right now, I guess. So there's sort of that issue as well.
Why is that?
Is it not going to only read one line? Because
Because we're defining the pull, right? So every time you pull, it's going to ask if the reader's ready, and if it is, it's going to read a line.
Yeah.
Otherwise, it's going to fail none, and then I think we'll just put this.
Oh, okay. I thought ready was like something. Is ready essentially has next?
I think it has next. Yeah, one of our symposium readers may be able to jump in here, and so now I think we just need to deal with the fact that we have this thing. So let's see. I think we could do Zeo.
A couple of chat things. So. Oh yeah, well, Naveed wanted to, okay, we'll show you tap again. Yes, I'm sorry, I did that too quickly. Chris's mind is blown. Because he understands it via the list example. That's awesome. And Francis Toth wishes he could be here with us, which is so sweet. And you certainly can, like totally. Francis, join us sometime if you want to talk about something or just hang out. That'd be super fun.
Yeah.
We'll talk about that. Reach out.
Yeah. And so this basically does it for us. So the only thing I've done here is I've changed the succeeds to attempts, which if you're coming from Zeo 1, that's just the, I think, better Zeo 2 name for Zeo.effect. So that's when you have something that could throw an exception. And then I'm just using this as some error operator, which is a really useful one. I think especially actually, this is a great use case for it, where I've got something that can fail with an E with a throwable here, but I wanted to change it to failing with a sum of a throwable so that I can compose it with this one that's going to fail with a none to signal a stream end. And
it's really just dot map error sum, right? Sort of a nicer version of that.
Yes, exactly. Yeah.
Oops. Cool. Hey, oh, now I'm mistyping everything. Rapport. All right. Wow.
So there we go. So there's at least intro to streams in a nutshell. There's.
Oh wait, now we have 0 minutes left. But we should make a file. Let's see.
Right. You want to see how quickly you can make a file?
I made a cool.txt if it works. Cool.txt. Here is a line. Here is another line. Come on. Let's have this. Here's a third line. Oh, it's okay. Fourth line. Fifth. Thank you. Oh, it's amazing. Eighth. Oh, 10th. This is amazing. I'm just going to let Copilot keep filling these out for me.
Okay, what's it called? Cool.txt?
Cool.txt, exactly. Do we need it? We might need to have like a dot. I don't know if we need the absolute path from this file or something, or from the directory. We'll see what happens. Maybe I can. Yeah, maybe we might need /source main Scala. Source/main/Scala. I'm not sure. I'm not sure quite how the from file works there from a string.
Okay, let's try.
And then we should call run head on that, or run collect.
Yeah, I'm just gonna call. Ideally we'd have like something called like run drain or something that would just
run it.
Say run it, but we don't care about the results, but we will do it. Look at that! Holy moly!
It works, amazing. And if I call like a delay on the Zeo effect of 1 second, can you just run that again just so we could sort of get that?
Yeah, definitely. Yeah, so we can get the big. Ooh, hold on, I got to shut there. Run that.
Okay, well that did not delay it at all. Actually, why didn't that delay it? Oh, maybe I didn't save. Huh? Can you try that one more time?
Aren't you delaying the whole thing versus you need to do?
I'm trying to delay the debug. Oh, because it's a tap, and the tap will not delay the.
No, hold on. There. Yeah,
oh, there we go. Cool.
Yeah, I think you had it outside of the whole thing, so you're just like delaying. Well, anyway, I'm not sure, but
hey, there we go. Now we're getting one line.
Yeah.
It's amazing.
Yeah, and so I mean, this is kind of amazing. Of like this stream now is going to describe opening the file. It's going to guarantee the file is closed when we're done. And it's going to give us this like stream of these lines that we can declaratively work with. We can say, use 3 of them or write them to another file. So it's pretty cool.
And it's going to
fly by the cool.txt.
And it's going to close the file for us when it's done. Deal with all that business.
Exactly.
Pretty fancy stuff.
Yeah.
Well, thank you, everybody. That was fun, and I think it was exactly 1 hour and 30 because we started a couple minutes.
There you go.
Perfect.
All right.
Amazing.
Thanks so much, everyone.
Yeah. See you next week.